give me a decent definition for a generic? As my computer freezes. Generics. What is a generic? A thing we can reuse again and again. Could you be a little more specific about that? What do you mean by that? Okay, a function? What else? Relates to a class? Okay. A way to categorize. Has anyone ever used the generic? Okay, where did you use it?
Stacks.
Stacks are a good example. Somebody. What did that generic allow you to do? How did you use it? What was it for? Shout it out. Way to use different types. Placeholder. Perfect. I think the most important thing about a generic is that it is a placeholder. Placeholder for items of, and here's where we'll be specific, any applicable type. So let's look at the first question. It uses some generics as placeholders for applicable types. Below is the declaration of the result type. Which are generics in this declaration? Phoenix. Success and failure. Cool. How'd you know that? So you've been able to put pretty much anything in the success or failure value. There is one restriction here. What is that restriction? Sunny? Failure needs to be of an error type. There is a restriction. Failure needs to be, so let's be a little specific actually. So, hold on one sec. Here's something fun. I'm sure we've seen it in our code. Error is actually a protocol, which is why we've never been able to create an instance of an error, but rather we've created maybe an enum with associated types like app errors or something like that. You need to conform to error in order to use errors, which means that for any of our failure blocks, we've been using something that conforms to the error protocol. So here, failure conforms to error. We're going to see this construction a lot, where our limitations on our generics are in terms of conformance. This is really a big protocol-based thing in Swift, is that we narrow the box of what these generics can be by saying that they must conform to protocols. How do we feel about that? going to squeeze it shut. So failure needs to be in conformance with the error protocol. Has to implement all that stuff. All right. So that is a type that uses generics that we've seen all the time. Here's another one. A dictionary. Adam, in this dictionary declaration, which of these like capital letter terms are generics? Adam. Key, so these first three options? Okay, let's see. So the struct itself, you're saying this thing we're calling a dictionary is generic. Okay, let's try it out. Let dict key or string to int of type dictionary. This is no longer really the way we do it. Let's make an empty dictionary. Let's see what they tell us. Oh man, hold on. Wake up, computer. Wake up, computer. All right. One sec. So dict dictionary. Let's go have a look at that thing. String and int we're able to use as generics. But let's look at this dictionary thing itself. Dictionary is actually just a type. It's a specific type that relates specifically to something from, actually from Foundation, so from something in Objective-C. And it's all set up and specifically implemented to work in a certain way. So what we'll typically see is that generics don't have a specific implementation. So a dictionary has a specific implementation. You can pretty much guarantee anything being declared as a struct or a class. There's an enum is not generic because that's just not fundamentally how they work. Instead, they're placeholders for things that we should hold somewhere. So our dictionary is that keyword dictionary. It's not generic. But value and key are. And what are the restrictions on value or key that you see here? Yeah, Aaron, what restriction do you see in this declaration to either of those generics, key or value? Yep, what does it say? You've got two generics, key and value. Those are the names we're giving to them as just placeholders. What does this declaration say must be true about something? Must be true of one of them.
Oh, that is hashable.
So what has to be hashable?
Key?
Yep, key. And in like regular English, that's exactly how we've talked about keys, right? Keys must be unique in a dictionary. Keys must conform to hashable. So they can be any generic type except that type must implement the protocol hashable. So it's pretty similar to using result. I can use any type at all as the value, which has the placeholder value in dictionary's definition. but the keys I use must be hashable. This is the actual implementation of something that we've, to this point, taken as fundamentally true. So dictionaries only require that their keys be hashable because in their actual declaration, it says you can use any kind of key except that key must be hashable. It's not magic. There's very little magic in Swift. All right. Questions so far? Cool. Now let's talk about some data structure. Has anyone ever seen this data structure before? Eric W., what is this data structure? Cool. So this is the definition for a stack, right? And the way we've normally implemented a stack looks something like this. We've said, all right, we've got a struct T. A struct that is a stack that takes in the type argument T. What is that T? Yep, T is any generic right now. T could be anything. There's no restriction on it. So we say that a stack contains the stack uses the type T, the generic T, as its elements. So it's got some items that are T in an array. It has this is empty, which is not at all related to T, which we could implement on our own. We can push a T onto the stack. We can pop potentially a T off of the stack or nil. And we could look at the top element, peek at it, and get potentially back some T or nil again. So let's look at this actual question though. Below is a stack Below is a stack implementation that uses generic items. Which of the following could you substitute in for T and keep it generic? You can use element. Can we use any of the other ones? Yeah. So there's something kind of fundamental going on here. What is element? Has anyone ever implemented element? What? Well, here's the thing is Ben didn't do anything special. All element is some capital letter placeholder type that isn't implemented anywhere else. So there is no class, there is no struct, there is no enum called element, which means that we can just use it as a placeholder word for our generic. We can kind of just use any word we want, so long as it's not implemented elsewhere. So that's how we indicate that we have a generic. Is we just use some word that's not used elsewhere. But if I had a struct called element, this stack, if I replace T with element, could only take in elements and only have an array of elements that you could push, pop, and peek at. So you can almost always use literally any word you want so long as that's not implemented somewhere as a type. So element is the only one of these that's not implemented. Knowing that, yep.
Is capital T defined in Swift somewhere, or is that just a capital letter that doesn't exist anywhere else?
The latter. T is not defined. So just like element.
So I could use capital E unless E is something else.
You could use capital E unless E is something else, yeah. The convention is T, or if it needs to like be descriptive, you'll generally have like key or value or element or something like that. Those words are ideally semantically helpful. Like they help you know what should go in there. Almost any capitalized word as my generic placeholder, so long as it's not implemented elsewhere as a type. Cool.
you tried to look up where that was defined, then
It would not give you anything. It would just show you the first place that T was used.
okay, that would be here in this case.
We got an element. All right, same stack. Knowing what we just talked about. Kimball. Below is a stack implementation that uses generic items. Which of the following could you substitute in for T and keep it generic? We can use item, yeah. Jocelyn, I think there are some other options. Which do you also think we could use? We could use thing. Awesome. Why can we use any of those? Okay, that's a good starting point. Let's get to sure. Why do you think you can use those? Okay. Well, what about those words is like popping out to you? Yeah, they're not specific. What might be another way of saying that in terms of like how your code is all laid out in files? Okay. Where is everyone? Oh, well. I'm going to pass it to Angela. Angela, why can we use thing, element, and item? Yeah, they're undefined. Let's be careful with that word just because in other languages it means other things. But undefined or not defined, anyway. Kevin? They are not native Swift types. I agree. But also they could have been defined elsewhere. So it's not just ints or strings, it could be any custom type that you have. So long as they are not defined, they can be used as elements. I'm sorry, say that again in the right way. So long as they are not defined anywhere, they can be used as your generic argument. All right, so I'm gonna pull this stack into our playground. Hello, stack. Thank you for joining us, stack.
Them being capitalized, is that just like the right thing to do, or is that like, well, work if it was lowercase?
Let's try it. So you see you're still getting the same blue highlight. And that's just because it's only by convention that we capitalize something like a stack or a strack, whatever you want to call it. We, as the people writing the code, have said, let's use this convention so people can recognize what types are. In the same way, for a generic type, we'd use capital letters just so that people understand this is taking in some generic type. So it's capital T for that reason. All right, so going back, I'm sure everyone's an expert in this already. Let's quickly implement push and pop. So Rod, when I push something onto a stack, what does that mean?
You are appending it to the stack.
Yeah, so I'm appending if I have an array, but let's say I had a linked list.
You are making a new reference.
I'm making a reference.
Putting it into the stack.
Yeah. And what's super important about that? How do stacks work? Can I put it anywhere I want, or does it have to go in a specific place?
You have to, I don't know how to explain it.
Cool. So we can only put it in one place. What would you call that one place?
On top of something else.
Cool. So I can only add to the top, let's say.
Yes.
All right. Who wants to give it a shot? How can we add to the top of the stack? Sure, I'll give it a shot. All right, so if I've got some item, it's that T. Where am I going to add this? I'm confused. Thank you. I'll use items. Items? Okay. All right, so I'm going to add it, I guess, to the end. Is it this? I think that's the wrong argument type. I'm going to add my element T. Cool. So it lets me add any T. I can do that in the definition here. That's great. All right. Eric M. What does pop do? Cool. I'm going to call it the top of the stack. But also, what does it do to the top of the stack? Yep. So it removes and returns the top of the stack. Cool. So I've been saying that the top of the stack is the end of the array. How am I going to get it? How am I going to remove and return the end of this array items? Items that remove. The array is items. Okay, we can do items.count -1. I'm sorry. Cool. All right. So I'm a little scared of this just because what might be the situation? What if I pop an empty stack? I could guard it. I also have, Swift did me a favor. Items.popLast. It was a really nice favor that Swift did for us. So you could totally do exactly what you're doing, but I could also just use one line to do probably what you were going to do before. All right, so if I want to pop off an item, I will remove the last item from the array items and either get back some element T or nil, because poplast gives me that. Let's go to question 5 here, though. Beep. Below is a partial implementation for a stack that uses generic items. If I wanted to add a peek function using an extension, what would its signature be? Let's go through the options. This first one, what does peek actually do? Looks at the top of the stack. Cool. And what does it tell us? Returns the value of the last element. So in our array implementation, yes, but in a kind of abstracted stack, it just tells us the top. It does not remove it, right? Cool. So would this peek do that? It would as long as there's something there. But I'm scared because what if there's nothing in the stack? Yes, explosion noise, that's right. So we probably want back an optional. So I'm going to delete, I'm not going to consider this first or this third option. Between the second and the fourth option, Jason. So I want to implement my peek here. Between the second and the fourth option, which function would actually give me the correct signature for my peek? Yep. I want the fourth one because it's an extension on stack. So this is going to be an instance method peek. extension stack. And what you'll notice is I don't actually have to I don't have to offer the type t as a type argument here for my stack because that already exists in the actual definition of this struct called stack. So I don't have to do this again. Say that again. So it's going to be the fourth one. Oh, yeah, I said it mixes up all the questions, which is great because then, only I know the answers. So this fourth one, peak, is going to have the signature no arguments, returning an optional t. And let's just look at that error again that I got for trying to tell the stack what its extension should be. Constrained extension must be declared on the unspecified general type stack with constraints specified by a where clause. So I could only create this extension for stack if I was going to further constrain what t is. If I was going to say, all right, we got a stack that can take anything, but if our stack is going to have, let's say, some function called func compare top and next, whose job is to return a bool, this function theoretically would compare the top and the item below it. Why? No idea. But it's a good point for us to be able to say, okay, we're extending stack t where t is equatable. And let's do this in the right way. Cool. So if I want to have the generalized generic definition of a stack using t, I can put all that in this struct, but this extension is specifically for one reason. So I can throw peak in that other definition, and then this extension is just adding functionality to only those stacks where t is equatable. So if I've got some type called class, or let's make it a struct not equatable, I can't make a stack not equatable nope, come back, not equatable, and then stack not equatable. Let's just return true here. Stack not. Oh, I love typing. Stack not equatable dot compare top and next. Boop up. There we go. Okay. So any stack can use all of the properties and methods inside of the initial definition, but only stacks that use the type t where t is equatable can use this one specific method, compare top and next. So I can't use this function if the type that I'm throwing into the stack is not equatable. If my type does not conform to equatable, then these functions are not available to me. So that's why we might extend a stack, is to say, hey, a stack should work this way when dealing with elements of this kind. So if I'm dealing with elements that can be compared, I should have specific functions where they're equatable, or I could just do that all. And here I could say, okay, any stack should be equatable. That's your choice depending on the situation, but you can do it in this way to restrict what kinds of stacks get what kinds of functionality. So if I change this, I said this is equatable, I would have to then implement the double equal sign, and then I could use this compare top and next. Go ahead. Static func. Right hand side, not equatable. Turning a bool. If I return true, I can use implicit return. Now I can use that function on this stack. Before my type here conformed to equatable, I could not. So let's put it back like that. Can't use because this specific type in the stack is not equatable. Okay? Neat. So, going all the way back, if we want to use an extension, I don't have to say stack taking in type T, but I might specify this extension is working only with that generic T where T is equatable. Amazing. Generics. All right. Having spoken about that, Jack, question 6 here. Below is the stack implementation that uses generic types. How could you reformat the first line to make sure that items in the stack can all be checked for equality?
How are they equatable?
Okay. Okay. Why not the last one? Yeah, I don't see any generic placeholder. Let's see if that can work though. Boop. Boop. So here's the thing. This can work. However, we're no longer using a generic. Equatable is not a generic, it's a protocol. So we are saying anything that goes into this stack must be equatable. It must conform to that, which is very different than having some T that is equatable. It's going to use whatever you put into this array as an equatable item. You would have to downcast to use it in some other way. You could further constrain T. Let's say we needed T where T is equatable and T is comparable. We have, by using a generic, and that's the wrong syntax, it's okay. By using a generic, we can continue to constrain T. We can say this type needs to be something specific, whereas if we only use equatable here, we are saying whatever's in this stack has to be equatable, and this stack is only equatable items. So equatable here is not a placeholder, it is not generic. It is a type of its own. Protocols are types. Amazing. Rocks my socks. Let's head back. All right, now let's look at just two more functions. Iram. True or false? The code below will allow you to use any generic type.
Are they equal? So T has to be, the generic type has to be equitable. So I would say false.
I agree. I couldn't put something that can't be compared into this function. Nice. And our last question. What is true of the generic T in the below function? It must be an int. It can be any type. It must be of a type that implements equatable. Nom, nom, nom. So nom, 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 question mark. T/F, nom, nom, nom. I'm going to go with F. Must it be an int? All right, I see head shakes. I'll take those head shakes. Why can't it be an, why is it not necessarily true that it must be an int? It's generic. Okay. So then can it be any type?
Well, that's like what Ron was saying earlier. It has to be a type.
So it can't just be any type. It has to be of a type that implements equatable. Perfect. Thank you, Phoenix. What are some questions you have about generics? They're a really powerful way to use these placeholders to extend our code. And also, you see them in the definition of pretty much any abstract data type, including arrays, dictionaries, anything you want to use. They use these generics to say, hey, you can use my data type pretty much however you want. That's pretty good. Questions? All right. Thanks, group.